All right, so now we're recording, and let's get started. More logic and framing. So the first thing that I want to talk to you about is different kinds of logic, because there are two main kinds, and we think about them differently, depending. So there is one type of logic called deduction, which computers are awesome at, just like think very logically. And then there's another type of logic called inductive logic, or induction, and computers are kind of horrible at that, but humans are great, and that's kind of what we naturally use. So let's talk about the difference, all right? And in the process, we'll talk about what it means to make an argument correct. Like, why is this thing that this person is yelling at me, why is that a good argument? Why is that a correct argument? When do I know it's completely incorrect, all right? So yeah, let's talk about the difference between deduction and induction, all right? So usually when you make an argument, it's got a bunch of pieces to it. And let's talk about the pieces finally. So you got some premises and a conclusion, all right? And premise just means assumption. So you have a bunch of assumptions that you're making as you're going about your argument, and then you're like using those to prove some conclusion. Like here's just a bunch of clouds. Here's premise 1 cloud, premise 2 cloud, premise 3 cloud. And then you have some conclusion. And in theory, your premises are all helping. I'll draw it in rainbow. Your premises are like the firepower that proves your conclusion. That's the idea. They're all helping each other. They're all giving rise to this conclusion that you're using to that you're really trying to argue. The conclusion is your goal, right? And you're using the premises as your assumptions, as your firepower. So your conclusion is only true under these assumptions, kind of thing. All right, I'll give you an example in just a second. Come on, slide away, little thing. It doesn't want to slide. Does anybody know how to make it slide? It just used to do it by default. Go back. Whoosh. It looks like it's trying to, but doesn't want to. So I'll just hide it again. Oh well. So all right. A deductive argument is when, there it goes. A deductive argument is when the conclusion is a certainty based on the premises. If the premises are true, then the conclusion must always be true. All right, and so hopefully this example makes it all clear. So here's an example deductive argument. It has two premises, so those are your assumptions. You're assuming you live in a universe where those premises are true. And then those two premises are being used to argue this conclusion, all right? So here is the argument. So premise 1 is it's sunny in Fresno. You assume that. That's an assumption, right? So if it's sunny in Fresno, and if premise 2 is true, if it's sunny in Fresno, then Lawton won't be carrying an umbrella. That's the other assumption, right? So premise 1, it's sunny in Fresno. Premise 2, if it's sunny in Fresno, then Lawton won't be carrying an umbrella. And then the conclusion based on those two premises is this. So Lawton won't be carrying an umbrella. Do you see how that's a correct argument under these two assumptions? Like, if it's sunny in Fresno, then I won't be carrying an umbrella. It is sunny in Fresno, so we can kind of plug it in and deduce that I'm not going to be carrying an umbrella, and that's a correct conclusion from those two premises. Okay? That's a bit weird looking, but are there any questions about that? That is the style of it. That is how deduction works. So assuming that these premises are true, the conclusion must always be true. That's what deductive means. Not sometimes, always. All right? So deduction is about proving things that are always true, right? Under those assumptions in the universe where those premises are true. There's also induction, and induction is the one where it's only sometimes true, all right? When you see induction, I want you to think like probabilities. All right, that's going to be the kicker there. And there's also something called mathematical induction. So if you're like a math major or you've taken a fancier computer science class, this has nothing to do with that. This is a different kind of induction, right? It's about arguments. So an argument is inductive when the conclusion isn't a certainty from the premises. It's just very, very likely, okay? So here's an example inductive argument. It's just got one premise, so assume this is true. Every time I've walked by that dog over there, it has not tried to bite me, okay? So that's your premise, that's your assumption. And then the conclusion in an inductive argument looks like this. So I'm concluding based on that premise. So the next time I go and walk over there by that dog, he's probably not going to try and bite me. right? So you see the word probably in there. It's not a certainty, it's just very likely. Maybe the dog has a bad day and he ends up biting you, but usually he didn't before, so he probably won't again, all right? So that's the difference between deduction and induction. Deduction, it's always true if the premises are true. Induction, it's just probably true, okay? Any questions about that? So computers are great at just plugging and chugging and figuring out certainties. Humans are better at induction, I would say. All right. Yeah, so just yell at me if you have any questions about this stuff. It's just kinds of arguments. And now let's get at what it means to be a good argument. All right, so we're going to learn some adjectives to describe arguments. Is it a valid argument? Is it a sound argument? All right, and soundness is stronger than validity. I'll tell you that right now. Stronger than validity. And so if it's sound, it's automatically valid too. So I'm going to teach you the difference and how to figure that out. And this will help you knock down somebody else's argument. If they are giving you an argument that's not valid, you can tell them that and be like, try again, it didn't work. If they're giving you an argument that's not sound, you can also call them out on that. And now you have words to describe why that person's wrong, all right, without just calling them names. So here is validity and soundness. Now, a lot of terms today. An argument, it's valid if it is impossible for the premises to be true and the conclusion to be false. So essentially, deductive arguments should be valid if they're correct. All right. So it's valid if it's impossible for the premises to be true and the conclusion to be false. And an argument is sound if it's valid and all the premises are actually true. Like these premises exist and they are true in the current universe. All right. So with an example, I think it'll make sense. All right. So it has to be valid first in order to be sound, and all the premises must also be true statements, right? So here is the standard sound argument example that everybody gets in a philosophy class. So here are the two premises, 1 and 2, and here's the conclusion 3. And 1 and 2 are being used to conclude 3, right? I'll use a line to separate the premises and the conclusion. That sometimes happens. So here is the quintessential sound argument. Premise 1, all men are mortal. Okay, so assume that, and then assume Socrates is a man, and then conclude, the conclusion based on those two premises is therefore Socrates is immortal. So not immortal, amortal. There you go. Therefore Socrates is mortal, and do you see how that is a valid argument? All men are mortal. Well, Socrates is a man. You can plug him into 1 and kind of use that to conclude that, well, because Socrates is a man and all men are mortal, then Socrates himself must have been mortal. Yeah? See how you're using that? So that is valid because it's impossible for the premises to be true and the conclusion to be false. So it's like, these are all true. It's impossible for this to be false, right? It's very easy to plug Socrates into part 1 and get out the fact that he's mortal. It all works out. It's a certainty, all right? Impossible for the premises to be true and the conclusion to be false. So it all works out. It implies it all. Assume we're in this universe, then this is true. The argument is also sound, in addition to being valid, because all the premises are true statements, right? It's not saying, assume that pigs can fly. It's assuming things that are true about our universe, right? All men are mortal. That is a true statement. Socrates is a man. That is a true statement. And so it's also sound, all right? Any questions about the differences? I do have another example, though. Does that make a little bit of sense? The more examples, I think, that'll help. So here's a valid argument, but it's unsound. So again, 2 premises and a conclusion. 1, 2, 3. So here is a valid argument. It's impossible for these premises to be true and the conclusion to be false. Like it perfectly implies the conclusion. So here is the premises. So assume that everybody who watched Hamilton enjoyed it, and then assume that John watched Hamilton, and the conclusion is then, therefore, John must have enjoyed Hamilton, right? Under those assumptions that everyone who watched Hamilton enjoyed it, you plug in John, obviously, he must have enjoyed Hamilton under those premises, assuming that they're true, all right? See how it's a valid argument? It all works out. The premises imply the conclusion, but it's not a sound argument because those are not true Those are not all true premises, right? Maybe John watched Hamilton, like that's a true statement. But is it true that everyone who watched Hamilton enjoyed it? There are some people without taste in the world, I guess. And so this is not a true statement because somebody who watched it maybe didn't like it. You see that? Though, if you assume this, pretend we live in a universe where everybody did like it, then it all works out. It's still valid, but it's not sound, okay? Because this is not true in our universe. We're being asked to assume something that isn't actually true, okay? We're just making up scenarios, all right? So that's kind of the difference between validity and soundness. Is it making a little bit of sense? Any questions about that? Because now I have questions for you. So I'll try to give you this on the same slide. But well, I guess I'm going to have to put it here again. There. Put it here for a second. But here, let's try this example. Is the following valid or sound? So this is another argument made up of two premises and a conclusion. All right. So assume 1, assume 2, and those are being used to conclude this thing. So is it valid or sound? So assume that all birds can fly, and assume that bats are birds. Is it valid to conclude that therefore bats can fly under those assumptions? It is. Question though.
I thought bats were not birds.
We're getting there. Good noticing that. Good job. So under these assumptions, assuming we're in a universe where this is all true, we're making assumptions right now. You can plug in bats here because apparently they're birds, and then you can use that to conclude that therefore bats can fly because we're assuming that they're birds and all birds can fly. Does that make sense? Any questions about that? So it's valid. Do we see that it's valid, at least? It all works out. It implies the conclusion. It's impossible for the premises to be true and the conclusion to be false. So it's valid for sure, but is it sound? And the answer is no based on that observation. Is it true that bats are birds? No, if you look it up on Wikipedia, bats are mammals, surprisingly. And then also, is it true that all birds can fly? Yeah. Chickens can fly for a little bit. That kind of counts. But I'm thinking penguins, right? Penguins can't fly, that's for sure. So neither of those premises are actually true statements. We were being asked to consider this. We're being asked to assume these things. Under those assumptions, sure, you can conclude this. But it's not a sound argument because these are not actually true assumptions in real life. Okay? So it's not a sound argument for that reason. All right? Does that make sense? So validity is like just play pretend maybe and see if it works out. But soundness is, are those assumptions actually true? Okay? Any questions about that? I think that's a good example to start us off. Because now I want you guys to try it for a couple examples. So here I've copied and pasted the definitions below. But please go to the by clicker page on our class website. And remember to sign in as well. I'll stop that soon. But take a minute to discuss with the people sitting next to you, say hi, and figure out if this is a valid or sound argument. Again, there's two premises and one conclusion. All cats are mammals, all dogs are mammals, assume that. Therefore, all cats are dogs. Is that a valid argument, a sound argument, both or neither? All right? So give that a try. It's a funny argument. And now, if it sounds weird to you, you have words to describe why it's weird or why it's wrong. Take another minute or so, get a good answer in, your best guess. Five, four, three, two, 1. All right, let's see what we were thinking. Valid, only valid and sound, or neither. Get something in the next few seconds while I move this to the next slide. All right. Ooh, do we have a majority? 10 responses, not a huge majority, but we're thinking valid. Let's take a look. All right, so it's valid if it's impossible for the premises to be true and the conclusion to be false. Like the premises, just assume that those are true, pretend we're in a universe where this is true. Do they imply that the conclusion is true? So it's like use these both as firepower. Does it follow that this is true? Right? So assume that all cats are mammals, all dogs are mammals, therefore all cats are dogs. Can you conclude that from those two premises? You said it's valid, so why can you conclude that? That doesn't really say anything about that they're the same, like they're the exact same, though. I know that they're both mammals, like I can conclude that cats and dogs are mammals. I can't conclude that they're each other, though. I don't think that's working, right? Like how can you combine those two somehow and end up with cats or dogs? I would need an assumption that's telling me something about all cats are, or I'd need a description of what it means to be a cat, not what it means to be a mammal. You see how it's kind of backwards? This is telling me about what mammals are, not telling me about what cats are or what dogs are. I can't conclude that cats are dogs or dogs are cats, right? Maybe if I had another rule where I said like I flipped these, all mammals are cats, and then all dogs are mammals, then I could conclude it. Does that make sense? That's a bit backwards here, though. All I know is that they're both mammals. It does not follow that all cats are dogs. So immediately, it's not valid. Are there any questions about why it's not valid? It just doesn't make sense. You cannot conclude that conclusion from those premises. They do not come together to imply that. If it's valid, could it be sound? Is it possible to be sound if something's not valid? No, it has to be valid in order to be sound. So the only possible answer is neither. Are there any questions about why it's neither? Just the fact that it's not valid. Those two premises, they do not conclude. They don't allow you to conclude this. It does not follow that all cats are dogs. If it was backwards, like all mammals are cats, because then you could, and then all dogs are mammals, but if all mammals are cats, then dog being a mammal being a cat would tell me that cats are dogs. That would have worked. But this is just telling me about what it means to be a mammal, not what it means to be a cat or a dog, right? That's probably still confusing, so that's why I have multiple examples. All right, let's try this one. So here is another one. Try this one. Again, we have two premises, one conclusion. Are they being used to prove that conclusion properly? So is it valid or sound? If someone was a philosopher. If someone was a philosopher, then they weren't a historian. And then Socrates wasn't a historian. So I'm concluding, based on these two premises, these two assumptions, that therefore Socrates was a philosopher. Does this imply, can you get this out of the first two? Can you conclude that, well, if somebody wasn't a philosopher, then they weren't, if someone was a philosopher, then they weren't a historian, and Socrates wasn't a historian, therefore Socrates was a philosopher. right? Weird words, because it sounds weird in English when you write logic things, but is that a valid argument? Is that a sound argument? Give that a try. This is definitely a harder one. All right, what are we thinking? Do you have time to get an answer in? Take a few more seconds. We'll look at it very small. Get your best guess in. If someone was a philosopher, then they weren't a historian. And Socrates wasn't a historian, so can you plug him into that if statement and like get out the fact that he was a philosopher? Does that all follow? Let's see. All right, this is a beautiful graph. Looks like we have a majority saying that it is valid, but maybe it wasn't sound. All right, let's take a look. Remember that it's impossible for it to be sound only. B could never be the correct answer. It's sound if it's valid. It has to be valid to be sound, so it's either both or neither. Okay, so all right, let's talk about this. So if someone was a philosopher, then they weren't a historian. This is an if-then. It makes more sense, actually, if we translate this to logic. So it's like saying, if philosopher, if someone was a philosopher, if that's true, then they weren't a historian. So if philosopher, then not historian. See how I'm converting that to logic? So you give me a philosopher, I will tell you, I give you proof that they are not a historian. That is the way the arrow works. And the idea is, now we know that Socrates wasn't a historian. We're assuming that. That's like, we know that not historian is true. Can you plug that fact into this one and get out the fact that he was a philosopher? Okay? And then use that to imply this. That's the main question, right? And a lot of us are thinking yes. I am unfortunately here to tell you that this was, again, a question where the answer is neither. So let me show you why. I know that not historian is true, and I'm kind of using that in this statement. I'm trying to go from that to philosopher, but that's the wrong direction for the arrow. This is an if-then statement. If you tell me that someone's a philosopher, then I'll tell you that they're not a historian. I can prove that to you. That's what the if statement's saying. But we're trying to go backwards. You see how that's not the direction that the arrow is going in? We know that not historian is true, and we're trying to prove that philosopher must have been true. When in reality, you could have had any other profession. Like you could have been a baker, right? It doesn't follow. You see how the if-then only goes one way. You tell me this, I'll tell you that. We're trying to go backwards. I know that not historian is true, and I'm trying to get out that philosopher is true, and it just doesn't work. That's the wrong direction for the if-then arrow. Are there any questions about that? It's a little tricky. If this, then that. You can only go this way. So if you told me that Socrates was a philosopher, then I could have concluded that he was not a historian. Then he would have been able to be plugged in, and you would have gotten that fact out. But you cannot turn this around. It's not the same statement. That would have been, if someone is not a historian, then they were a philosopher. It's a different if-then statement. It's a different direction. All right? So again, it's not valid, and so it can't be sound either. So the answer is neither. Any questions about that? Again, tricky. I have one more for us. See how hard it is to figure out when something is really following from something else? That's why I'm giving you these examples now rather than on a test. Get some examples. Get some practice. All right? Here's the last one. I'll start it again. This is near and dear to my heart, of course. So I love salsa. So here is your last argument question. So all computer scientists like to dance salsa. I know I do. Assume that. And then assume that some men are computer scientists. All right. Under those two assumptions, can you conclude that some men like to dance salsa? All right. Use those, and I think I started it right. Take a minute to see if that is valid, sound, or neither. So does it follow, and are the assumptions true? There's kind of some arrow relationships, like some if-then, like if you're this, then you like this, right? Maybe draw those out and see which direction you want to go in to make sure it's the correct direction. And let me if you have any questions. Take a few more seconds to get in an answer. Got like 5 seconds left. All right, that is my timer. Let's see what we're thinking. Surely the last one is not a trick as well, or not a hard one. All right, do we have a slight majority? Not quite a majority. We're thinking A, though. C and D. Now we're never guessing B again, which is good. That is progress. So, all computer scientists like to dance salsa. So if you are a computer scientist, this is kind of saying then you must like salsa. There's an arrow going in that direction. Do you see how I'm imagining that? Does it make sense why that arrow is going that way? You give me a computer scientist, I'll tell you that they like salsa. That is kind of an if-then statement. It's an arrow. That's the way the proof is going. You give me a proof of this, I'll give you a proof of that. All right, then some men are computer scientists. So like, not every man, but you give me a few men, then certain ones of those are computer scientists, right? And then we're trying to conclude that, therefore, some men like to dance salsa. Does it follow from those two arrows that some men like to dance salsa, right?
Yes.
It does, because some men are computer scientists, right? And then some computer scientists, you can link them right here, right? Now that you know that some men are computer scientists, and all computer scientists, we're assuming, like salsa, then you can conclude from that, by linking those two, that some men like to dance salsa. Because some men are computer scientists, and we're assuming that all computer scientists like to dance salsa. Any questions about that? So that is a valid argument. So we see why it's at least valid. Any questions about why that follows from those first two? Now, the question is it sound? All right, so we check, like, are some men computer scientists? Sure, that's fine. But do all computer scientists like to dance salsa? I don't think so, right? I think I'm definitely in the minority there. So it's not a sound argument because that's not a true statement, all right? But it is valid. Under that assumption, it is true. You can conclude this, right? It makes sense. And so it's a good, valid argument, all right? Valid only, though. So the answer is, in fact, A. Good job. Any questions about that? That is validity and soundness. So do the premises come together? Does the conclusion follow from them? That's validity. And then are the premises also true? That's soundness. All right. Are you ready to keep moving? Because now I want to talk to you about how to put, like, what these arrows mean. Like, I've just drawn them. Let me teach you the logical version of, like, if, of arrows and things like that. Because that's where we need to go. All right. So, yeah. Again, we're going to logic because English is very ambiguous. You remember the or example, right? So let's learn what if really means. Let's try and write a truth table for the if statement, for a sentence with the word if in it. So let's use this as an example. Let's pretend that Dad tells us on the weekend that he'll give us $20 if we mow the lawn, all right? And so this is an if statement, right? This is a logical if. It's like, if you mow the lawn, you do this. then I'll give you $20. It's kind of an arrow going backwards. If you do this, then I'll do this for you. Okay? There's an arrow kind of going there. And so we're going to try and figure out under which conditions would we feel cheated if we didn't give the $20, because that's what false is, right? We're trying to come up with the truth table, and false is equivalent to when someone's lying to us. False is when you were lied to, and we'll just assume that the other cases are true. That's how we come up with this logical operation called if. So under what conditions would we feel cheated if we didn't get the $20? So here's all the options for us mowing the lawn and getting $20. Those are two different things, right? So mow the lawn could be true and got $20 can be true. Any combination of those two, all right? And so under all of these different combinations, let's try all four of them. In which cases would we feel cheated by Dad? He told us this. He's promising us all this. I'll give you $20 if you mow the lawn. Which cases would we feel cheated? And this is the one case. So let's talk about the other ones first. So if we mowed the lawn and we got $20, then we do not feel cheated. We upheld our version of the bargain, and so did Dad. We got our money, right? So that's fine. No problems there. What about this case? If we didn't mow the lawn, but we got $20 still, then Dad was still telling the truth. He wasn't lying to us because we got money anyway. It was just nice, right? So that case is fine. And then this last case is also fine. If we didn't mow the lawn, but we also didn't get $20, then we don't feel cheated by Dad for telling us this, for promising us this, because we just didn't do the work. We're not getting $20 for free. That's fine to be in that universe. Okay? The one combination of mow the lawn versus $20 where we feel cheated is when we did mow the lawn, but we did not get $20. Do you see how that's the one case where Dad was really lying to us? He promised us this statement, right? Then we totally feel cheated here when we upheld our end of the bargain, but we did not get the conclusion that we were looking for, right? We did this, but we didn't get this. That's the one time the if didn't make sense, okay? And so that's going to be the one case in our truth table when we're going to make a logical version of if, when it's false, right? It's called implication. That's the fancy word for an if statement in logic. If A is true, kind of add an is true in here. If A is true, then B is true. Is true. Okay, so implication is just the logical version of an if-then statement. It's called a conditional in programming. It's like your if-else block. So it's always something on the left. That's your hypothesis, the thing you're assuming. And then the then is on the right. That's what you're concluding. Okay, so it's very similar to what we just talked about, our arguments. And so we just learned the truth table for implication. And I want you to read this symbol, this double arrow. You can also use a single arrow as if A, then B. If A is true, then B is true, all right? And so you can think of A as like mow the lawn and B as got $20, all right? So this is the one case where it's false. A implies B is false. If A, then B is false. If A is true and B is false. That's the only time that you end up with false. All right? Every other case, you weren't feeling lied to, all right? And so this is what we will define the truth table to be. It's always true except for when you upheld the hypothesis, but you did not get the conclusion, all right? And so if you're trying to prove this to somebody, if you're trying to prove to somebody that the statement, if A, then B is true, then you have to show that it's impossible to get here, right? Because that's the one way to make it false. You have to show that it's impossible to fulfill the if side and not get the then side, all right? You can alternatively think about it as like, if I give you A, there's like an arrow involved, right? If I give you A, then you have to give me B. That is what you're promising in an if-then statement, all right? Any questions about that? So that's just a new symbol, and here is its truth table. If A, then B. It has to do with, go back to this definition of being lied to. I think that would be a good example. So this is like mowed the lawn, and this is like got $20. Right? So come back and check that. And now we can talk about deduction again. Deduction is logical. It all works when the two premises, or however many there are, imply the conclusion. Here's what's going on, right? Let's translate this and learn why it's valid, why this is a valid deductive argument. So all men are mortal, Socrates is a man, therefore Socrates is a mortal. If we convert that to logic, here's what's going on. The first statement, all men are mortal, is saying if man, then mortal. Do you see that? That's the trick. And so there's really an if-then statement. If you're a man, then you are immortal. There's your A and B. All right? So we're assuming this is true, right? And we're assuming man is also true. It's like Socrates is a man. And we're trying to prove, therefore, these 3 dots mean therefore. Therefore, mortal is true. See that? That's what the argument really is. All right? And we're trying to prove that this is logical and valid. Well, the way that you can get that with logic is by looking at the truth table. The conclusion, the thing below the line, conclusion follows from the, what's the word from, sorry, from the truth table for implication. So let's look at it. We're assuming that if man, then mortal is true. So pretend that A is man, B is mortal. We're assuming that that's true, so we're in one of these 2 statements, right? We're assuming that if man, then mortal is true, so we're in one of these 3 cases, right? We're assuming this is true, so we must have been in this case, or this case. Does that make sense? So we're under that assumption. Then we're also assuming that A, the thing on the left, man is also true. Assume that that's true as well as the implication itself is true. So what are the only cases in the truth table where this works out? So assuming that the whole thing is true, right? A implies B is true. That's one of these 3 cases. And then we're also assuming that A itself, that was the man part, is true. And here are the 2 cases where that's true. And the only time when they're both true, we're assuming that we're in a universe where both of those things are true, is this line right here. You see that? That's the only time where A implies B is true and also A is true. And what happens, we're trying to conclude that it's always true that mortal, the thing on the right, the B, that's also true. Do you see how in this one section of the truth table where we are guaranteed to be now under those assumptions, B is true. So mortal is true. All right? So that is why it's a valid argument. So you shrink down, if you zoom in on the pieces of the truth table where it matters, where all the things that we're assuming are true are actually true, then look in the column for this thing and see what it is. If it's always true, then this is a safe conclusion. All right? So we looked up, we noticed that we must have only been here, and our B was also true, and that's what we're concluding, and so it does follow. This is a valid argument. Okay? Any questions about that? That's how I read off the truth table that this all works out. That's why deduction works and makes sense. It's always true that the conclusion is implied from the premises. And that's why I use the word implied, because it's all about implication. Logical implication. Am I good with that? All right, so it's just another symbol. And every symbol has a circuit diagram. Can you draw a circuit diagram for implication? Like you have an A and a B, and you have some weird jumble of things that together give you out A implies B, whatever that result is. Can you do that? Sure you can. Because anything in logic is equivalent to some combination of and, ors, and nots. So it just so happens that A implies B is equivalent to not A ORed with B. Now let me show you that. I'm going to show you that the column is going to be the same if I do it this way. I'll get true, false, true, true again. So not A or B. So not A is false. ORed with B, though, that makes it true. Again, not A is false. ORed with B. Oh, shoot, it's false or false. That's the only time it's false. And then not A or B, if I'm doing not false, that makes true. If I'm ORing true with anything, it's automatically true. True and true. Because not A again. Cool. So this is how you could make a logical circuit. You could make a circuit diagram or an actual circuit from wires with just a NOT gate and an OR gate. Okay? So that's how you could form implication in circuitry. Any questions? Yeah.
So if A is not A not B, right? So how is the first one true?
How is this one true right here?
Yeah.
Okay, so not A ORed with B. So not A is false, right? So that's false. And then we're ORing it with whatever B is there. And B is true. So it's false ORed with true. And if you look up the truth table, anything, if you have true on any side of an or, it's true. Okay? So yeah, just go back to the or truth table, and you'll find that anything, if there's a true on any side, the whole thing's true. Okay? Other question. A and not B, that would be a different truth table. It would be this one. False, false, false. Which is like the inverted version of that. You could negate it, and that would make it the same, but then you've just added another negation, so it's extra cost for your circuit. But yeah, that would also be equivalent if you wouldn't negated that. Yeah, good point. Any other questions, comments? Yeah, these are good thoughts. All right. Yeah, because maybe you're done with symbols for the day. I have 2 more sections to these slides, and neither of them have a ton of symbols, just pictures in the last one. So I made a typo and I said farming instead of framing, but I kept it because it was cute. So framing is the next topic, and this is just a single slide. It's going to be very obvious, but maybe we've never heard this before, and so let me tell you. So when you're arguing with somebody and you feel very strongly about your side of the argument and they feel very strongly about their side of the argument, and neither of you can come to a consensus, like it's my way or the highway kind of thing, the other person is not seeing your point, but you are so right, it's just obvious that I'm right. Let me tell you why that other person can't see your point. Why it's clear that your point is not true to them. All right? It's all about this thing called framing, or the frame of reference that this person is in, all right? That you're in as well. It's all about how you view a situation. So it's your frame of reference on the situation. So your frame of reference, it shapes how you view the world. So another word for frame of reference is your worldview, all right? We all have different worldviews. Does that make sense? So that's going to shape how you view the world, and also the assumptions that you're willing to make about things that you're hearing about. Okay? And so it's your worldview. That's another word for frame. Your worldview. And it's all about terms, right? The way that you think about, when you hear a word, what does it evoke in your mind? It's not like the denotation of the word, it's the connotation of the word. If you remember that from an English class, right? So the idea is, if you can control somebody's frame of reference, if you can control the frame in which you're discussing things, then you can control the entire argument, because the words will sound different and it will mean different things because they have different connotations, and they'll evoke different feelings from somebody who has a different worldview. All right. And this is the reason why someone could have the exact opposite viewpoint as you on a topic and also justify it, is because they have different words to describe it and a different worldview to go along with it. All right. So the standard example of this is politics. Let's not have a huge debate in this class, but if I zoom in, I think you'll get the idea very quickly, right? You can usually separate people into left-wing people or right-wing people, and here is just very, very simplified versions of different topics that they might argue about, right? If you're left-wing, you might say the word pro-choice. If you're right-wing, you might say the word pro-life, and just immediately, in using those terms, right, they say something completely different. And so you see how if somebody's thinking in terms of pro-choice and the other person's thinking in terms of pro-life, they are never going to agree, right? Because their worldview is different. The terms that they're using are different. They evoke different feelings. Okay? Any questions about that? It's like with other terms as well, like single-payer healthcare versus socialist healthcare, right? Again, this is just very, very simplified. But if you read a few of these, I think you'll see why nobody can agree. Public service versus big government, all of those things. Okay? So that's gross oversimplifications of how people think, but do you see how the different word choices, depending on your worldview, can influence how you think? The words that you were taught when you're learning about these arguments are going to influence how you think, and how the person who you're arguing against will think. So that's why you can never come to an agreement sometimes. That is your frame of reference or your worldview. All right, any questions about that? Very philosophical for that little subsection. But yeah, that is frame of reference. If only we could all just understand each other and get along. Finally, I have one last technical topic for the day, and let's see if I have to do anything else. Let's not forget. Okay, no new essay, just a programming assignment, but that'll be next time. So, last topic for the day is called state machines. It's a fun little concept that is going to help you write really correct programs. All right, if you can break something down into a state machine form, I promise it's going to be a very easy program to write. All right, so this is one way. There are many ways to think about computation. It's a way to break down a problem and just the process of computing some answer. Right, so let me show you that. And so obviously the study of this is the study of algorithms. Like you're trying to come up with some answer, some method of doing something, some recipe to get out a final answer. And one way to do it is to use this thing called state machines, which allow you to break down computation to like do step 1, then do step 2, then do step 3, and then you'll get the final thing that you really wanted. All right, this is all very vague, but it'll be concrete on the next slide. So yeah, how can you break down computation? Here's one way. It's called a state machine, right? And a state machine abstracts away the kind of computation that you're trying to do. Just draw a bunch of circles and draw some arrows between the circles. You can translate this pretty easily to code, all right? So a state machine looks like this one or this one. I'll zoom in a second. And the idea is, in your program, or just in this process that you're trying to describe, you're always in some state, like you have to be in one to start, and then you're moving around between them. And then you can move to new states, new bubbles, via transitions. All right, so computer scientist is just a bunch of arrows and circles. Here we go. So here is the first state machine. Let's pretend that when we're born at home. So there's like a concept of a start state. This is a state machine that models a human. All right, it's the easiest first example. So let's pretend that we start our life in the home state and we have a very depressing life. All right, we wake up, or we're just immediately awake, and it's time to work. And so we want to transition to the work state from the home state. And the only way to do that is to follow this arrow. It's constraining the ways that we can compute things, the ways that we can move around inside of this program. So the only way to get to work is to take the train. And so if we do that, now we're in the work state. And then maybe we work and it's time to go home. And so we'll take the train back to home. So that's the one arrow that'll get us back home. There's only one way to get there. Okay? So it's constraining what we can do. And then maybe it's bedtime and we'll sleep. And that puts us in the bed state. And now we're in the bed state. The only way to get out of it is to go back to the home state by waking, right? That's the other transition to follow. You see how you can move around by doing these different actions, and that tells you where you can go and where you can move. So you're always in a certain state, and you can move to other states via these transitions with labels, all right? So maybe it's like, maybe you go to work, and then you forget something at home. So you go back on the train, and then you go back to work twice. You don't have to follow it. You can follow this in any order, right? Maybe it's the weekend, and so you're in the home state, and you just stay home twice for 2 days before it's work, right? You can move around following these arrows in any way, and that's telling you all the valid ways that you can act, right? Notice that it's impossible, and it's very clear from the diagram that it's impossible to go from the work state to the bed state. There's no bed at work. There is no arrow like this. You see that? That's constraining what we can do, and that's very powerful, to be able to list exactly what you can do at any point in time and the ways that you can move around between actions, right? So that's a state machine. Any questions about this one? It's very simple, but I hope that the diagram makes enough sense. Yell at me if it's not. Let's go to one that actually is for a program now. So that's a silly first example. Let's talk about a more normal example that you might see in code. So here is a example that maybe is how like Uber or Lyft models the computation in their app when you're taking like a taxi or you're hailing a ride from somebody. So let's say that when you open up the app and you click, hey, I want a ride, you move into the trip requested state. And that's where you start inside of your program. You start in the trip requested state, and then it's not going to give you a driver until it tries your credit card, right? And so it's going to go to the payment state, right? Payment requested. And now it's sitting in the payment state waiting for like Visa or MasterCard to respond to Uber servers. And so it's sitting here. until it can make your payment work. If it fails, if it ends up failing, then it's not going to alert any drivers, right? You go back to the trip requested state. Maybe it tells you to enter in a new credit card. So you see how you can never get a driver if the payment fails. It has to succeed, right? The only way to move to the driver success or driver assigned state is for the payment to succeed. For you to transition from payment to driver assigned, the payment must have succeeded. So that's the only way you can get something is if you paid for it. You see how that's constraining your program, making sure that you've paid before you get a driver assigned to you? Does that make enough sense? So now I'm sitting in the driver assigned state. The driver might be like, that's too far, and cancel the trip, and then you go back to the start. Or they accept your trip, and then you get in the car with them, and then the trip is over. They click a button, and then the driver goes into the unassigned state, and then it's like trip end, and then it all starts over again. Okay, but do you see how this is constraining what you can do inside of the app? It's making sure that you can never get from the trip requested state to the driver assigned state without succeeding in paying for it. You see that? That's very powerful, and it's apparent from the diagram that it's impossible for it to not work out. And so it's very easy to translate these diagrams to a program, and it's then pretty easy to notice that they're working, assuming they're following the diagram and doing the right thing. Okay? So that's a state machine. So you got your states, those are your bubbles, your circles, and then you move to other states via transitions. There may be multiple transitions, just with different names. They're all labeled usually. So yeah, that's how you write programs. If you notice that a computation breaks down in this way into like states and ways to move between them, totally reach for a state machine because it's going to make a very easy program. All right, so yeah, here's the name of the game. Group your program into states and actions on those states that maybe move you around. All right. So here's another silly example for humans. Let's pretend that I'm going to make a state machine for you as students to describe you. All right. As a student, I think of you as a two-state machine. You have two states. You're either in the learn state or the practice state. All right. And when you first get into this class, I haven't assigned anything yet. So your start state, your initial state, is learn. And so I'll mention that by drawing an arrow from nowhere. That means that this is your start state. That's where you begin your life in the program as a student, I guess. And then you're going to alternate between the learn state and the practice state as like I post you assignments, as lecture starts, as lecture ends, things like that, right? So like when an assignment gets assigned at the end of class, you're going to move from the learn state to the practice state, I assume, right? And you're going to keep on practicing. You can have transitions that keep you somewhere as long as the assignment's not done. And then when it's lecture again, you have to go back to the learn state and listen to me, right? And then you should stay in the learn state, I assume, while the lecture is not over yet. So that is the kind of diagram that you could describe yourself with, assuming you do nothing other than study. Okay? Does that make sense? That's how you can draw a diagram for you. And then there's also a concept of final states, like states that you want to end up in, and call those successful states. So at the very end of the class, like I give you the final exam, there's nothing left to learn. So the final state, and you can reference a final state and mark a final state by making two circles. So the final state is going to be the practice state. Because you're taking the final, and that's where you stop. The class ends after you take the final, and you were stuck in the practice state at that point, because you're practicing all the things we learned. Okay? So that is how you can model things. It's just a real-life process with a state machine. Any questions about that? So you got initial states, final states, you can have multiple, and then transitions between the states, and they're always labeled. Like, how do you move? How do you move around? All right? Any questions about that? So I'm going to teach you the coolest state machine that actually performs computation now. It's actually a state machine that I learned in my first computer science class in college, so I'm just passing it along to you guys. It is a state machine that counts words in a sentence, all right? And we're going to see how very easy it is to make this work, all right? So let's say that we're getting something from the user. They're typing a sentence, and we want to count all the words in that sentence. Like we're making Microsoft Word, and we want to do like the word count functionality for it. And so let's pretend we're using it Scratch to do all this. Like, hey, user, type a sentence. That goes into the answer variable, right? And let's pretend that the user is very weird. Like they type, I'll use this symbol for space. Like they type space, hi, 2 spaces, and then mom, so hi mom, exclamation point, another space, and that will be what they type. Do you see how it is non-trivial to figure out how many words are in this string of characters? Because maybe if you just counted the spaces, that would be an incorrect answer because the user can type as many spaces in a row as they want. Like this is 1, 2, 3, 4, and you'd be like, there were 4 words. Spaces don't just have to delimit words, right? You can put as many as you want. And you want to give back that there were only 2 words here. You want to solve for 2. It should work for any string with any number of spaces. I'm going to count all the words in this string with the state machine. And so here's the idea. We're going to read these characters. We're going to go through them one by one. Look at the space, look at the H, look at the I in order. And we're going to run them through a state machine. That's going to be how we transition. Which character we saw is going to transition us. And the thing to notice, the key idea that's going to work out here is that when you see a space character, that means you're in between words. All right? That's key. White space separates words. And then when you see a non-space character, it's either part of a new word, like if it's the first one, or it's part of an existing word that we've already counted, right? So the I is already part of the high word. But the H, that's a brand new word. It's the first character that starts that word. So we need to differentiate between those things, all right? So here is going to be the state machine. We are either in, we're going to make a 2-state machine. We are either in the outside a word state or the inside a word state. And this will make sense in a second. Outside a word or inside a word. Okay. And here's how we're going to transition. If we are outside a word and we see a space character, are we still not in a word yet? See a space. See how that? We're still outside a word as long as we keep seeing spaces. So we should stay there. That makes sense? So just keep on staying in that same state. You are not inside of a word if you keep seeing spaces. And then same if you're inside a word and you keep seeing non-space characters. See non-space. It's like if I'm marking that I'm inside a word like high and I see the I in high, like I still am inside a word if I see a non-space character. And then we can transition, right? If you're outside a word and you see a non-space character, you've just started a new word, right? See a non-space character. That begins a brand new word. And then maybe you'll see a bunch of those and stay inside of that word. Or you're inside of a word, like you see the I, and then you see a space, and that marks the end of that word, right? Now you're outside of a word again, if you see a space. So I hope these states and their transitions make sense. But here's the idea. Every time we see a non-space character, we would like to add that or count that we saw a new word. So we're going to keep like a count variable for the number of words we found, start at 0, and increment it slowly. And let's figure out when we want to do that. So let's walk through this. So the idea is we're going to put every character, we're going to run every character through the state machine, one by one. And our start state is going to be outside of a word. Since we haven't read anything yet, we're not inside of any words yet. So at the very beginning, we're outside of a word. And now we're going to read every character in order and run it through our state machine and watch it work, right? So the first character is a space character, and so we stay in the outside of word state. All right? Then we see the H, and we just saw a brand new word, right? Now we go from outside a word to inside a word. Now I'm in the inside of a word state. So it makes sense how I'm transitioning? Any questions about that? That's key. So now I'm sitting in the inside of a word state, and then I see an I, which is again a non-space character, and so I'll stay in the inside of a word state. All right? But then when I see a space, I'll transition to outside a word. I was here, now I'm going to go here. Now I'm outside a word. Then when I see another space, I'll stay there. I'll continue to be outside of a word, right? But then when I see the M, that marks a brand new word, right? Now I go from outside to inside. And so I see the M, now I'm inside a word. I see the O, I'm still inside a word. I see the M, still inside a word. See the exclamation point, still not a space character. So I'm still inside of a word. And then finally I see the space at the very end, and then that will move me from inside a word to outside a word. So that's how I'll end. I'll end in the outside a word state. And then the question was, Now the question is, when do I see brand new words? When do I want to add to my count? Which transition marks me seeing a brand new word? Which of those four?
From inside a word to outside a word.
Not quite. I think you have it backwards. It's going to be outside to inside. Let me show you why. So definitely try it the other way, because I think, yeah, there might be some issues with the last one. Because if I got rid of this space, that's the reason why this wouldn't work. Because then I wouldn't have counted it, right? If I stay in the inside a word state, and that's my last character, I'll be an inside of a word, but I wanted to count that as a word. So that wouldn't work out. It's got to be this one. So every time I see a non-space character, that means I wasn't inside of a word, but now I am. That's the first character of a brand new word, and I better count it. That's the idea. So if I do that, here's how it works. So I start in the outside of word state. I'll just run it quickly now. Then I transition along this transition. I saw a non-space character. That's my H, the first character of a brand new word. Now I'm inside of a word. And if I just program that to add one to my count whenever I follow this arrow, then, oh man, it's going to count all the words. So then I, still non-space, keeps me here. Then space transitions to outside of a word because I saw a space character. I followed this one, right? Another space keeps me there. But now I see an M, and so I was outside a word. I see a non-space character. That's going to bring me to inside of a word and increment my count. Ooh. And then O still inside of a word, M inside of a word, exclamation point inside of a word, space. Then I go from inside to outside, but of course I don't count anything because I haven't seen a new word yet. So every time we see the first character of a word, I'm going to add to count, and it doesn't matter how much the user tries to trick me with their space characters. They can type 1,000,000 if they want. This is always going to correctly count how many words are in a string of characters in a sentence. Are there any questions about that? This is a useful thing that we'd want to program. That is pretty much how Microsoft Word is counting the number of words in your text file, or Google Docs is, or whatever. That is the correct algorithm. Are you good with that? This is definitely fun. Definitely study it. Yell at me if you have any questions about it. But that is the example. Yeah. So thank you all for coming and watching me on Zoom if you wanted to. And I think that's everything that I wanted to record.